Hello, everyone, and thank you for joining us today. My name is Lou Parrish, and I will be your host for this webinar on the self-cleaning seals technology sponsored by NASA's Technology Transfer Program. In my job as a Senior Technology Transfer Specialist, I support this program and work with NASA scientists who have developed new technologies that may have applications outside of the aerospace industry. We patent these inventions and market them to industry through our website, which I'll show you later, as well as through efforts like today's webinar. Our presenter today is Dr. Aaron Olson. I'd now like to give you some background on our presenter. Dr. Aaron Olson is a physicist at the NASA Kennedy Space Center in the SwampWorks Electrostatics and Surface Physics Laboratory. Dr. Olson works on lunar in situ resource utilization, or ISRU, and lunar dust mitigation technologies in support of the Artemis program. In 2023, Dr. Olson was named a Future Technology Leader by the Engineers Council. Aaron was born in Kikwit in the Democratic Republic of the Congo and was raised in Madison, Wisconsin. He earned a BS in Mechanical Engineering in 2012, completed his MS in Engineering Mechanics in May of 2014, and a PhD in the same field in 2018 from the University of Wisconsin. As a graduate student, Dr. Olson was a NASA Space Technology Research Fellow and collaborated on lunar ISRU research with NASA Kennedy Space Center's SwampWorks lab. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box, and we will answer them during the Q&A session at the end. At this point, I'm going to turn it over to Dr. Olson.
Thank you for the great introduction, Lou. I appreciate it. And good afternoon, everyone. I appreciate all of you for taking the time to dial into this webinar. And I look forward to giving this presentation and hearing your feedback and any questions you might have. I'll go ahead and share my presentation and dive right in. If there are any issues with the presentation or the format as it shows up on your screens, please let me know. Otherwise, I will go ahead. All right. My name is Aaron Olson. As was mentioned, I am a physicist in the Electrostatics and Surface Physics Lab in the SwampWorks series of labs here at Kennedy Space Center. I'm joined as a co-author on this presentation by Dr. Charles Buehler, the lead of the ESPL lab here at Kennedy Space Center, and Dr. Crystal Acosta. Both of them and many others within the ESPL lab have made major contributions to the work that you will see this afternoon. Self-cleaning seals for harsh environments. Within this presentation, I'll give you a bit of a background on the problem of dust and why it is we need to develop a technology such as this. I'll give you a bit of a background as to a solution that was developed for space here at Kennedy Space Center within our ESPL lab. I'll go into a few different concepts that were developed to bring that technology solution to the environment of seals. And lastly, I'll give a summary of the presentation, some acknowledgments, and leave time for any questions you might have. To start with, as some of you might know, dust during the Apollo missions in the 1960s and 1970s was a major issue that the astronauts and their equipment had to deal with. You see some images here on this slide of the Apollo 11 lander, the Apollo 15 lander, and an inside shot of the Apollo 17 lander with astronaut Parrish and Schmidt. You can clearly see that his suit was substantially fouled by abrasive and electrostatically charged lunar regolith. This dust caused a number of issues, from contaminating sample containers that needed to bring material back to the Earth, along with degrading the sealing capability of the EVA hatch that basically preserved the environment of the lunar landers while they were on the surface. And one critical case that hasn't gotten a ton of attention, but I'd like to bring to light today, was the case of Pete Conrad's suit in the Apollo 12 mission. His suit, which had conducted 2 EVAs, was essentially leak tight before his first EVA, but after those 2 EVAs developed a leak of approximately 0.25 psi per minute. the safety limit for that particular suit was 0.3 psi per minute. Add Pete Conrad needed to do an additional EVA as a part of the Apollo 12 program, and obviously a corollary to that would be the new spacesuits that will be a part of the Artemis program going forward, will have substantial issues. There are a couple research papers that I would like to point you all to. One is from Jim Geyer at Glenn Research Center that talks about the effects of lunar dust on EVA systems during the Apollo missions and gives an in-depth look at all the different issues that not only SEALs, but other areas of technology had because of, again, the abrasive and electrostatically charged dust that occurs on the surface of the moon. Additionally, some work has been going on at Glenn Research Center over the last few years to characterize just how dust-tolerant conventional sealing technology is, giving some information as to, again, the reason why we need to come up with solutions to make sure that dust does not hinder the performance of SEALs on the lunar surface. I'll move forward. A technology that's been developed as a dust mitigation tool by our lab here at Kennedy Space Center is called the Electrodynamic Dust Shield, or EDS for short. The video that you see here is an example of the technology implemented on a clear plastic substrate where there are embedded electrodes of indium tin oxide, or ITO, traces that are transparent to the eye. This is a three-phase embodiment of the EDS, and effectively what you see here is alternating high voltage being applied in these electrodes, creating a electrostatic or electrodynamic field that repels the particles off of the surface. This is done with a high voltage power supply. There are many formats that have been developed at our lab for different solutions of the EDS. One example here is a two-phase high voltage power supply that can be as compact as approximately 5 by 5 by 2 centimeters. The power required to clear dust off of a lot of these EDSs that we've developed is typically on the order of milliwatts. The supplies themselves, because of the switching electronics and everything else involved, typically draw less than 10 watts depending on the application. These supplies have been made as light as just under 60 grams. The high voltage output can vary between 1 through 4 phases. Depending on the application, you may only need 1 phase and a ground plane, and some other applications you may want 2, 3, or 4 phases depending on what you're trying to accomplish. The waveform amplitude required is typically greater than plus or minus a kilovolt, and we normally operate these systems with a 10 hertz square wave with extremely fast rise times on those square waves. Waveform optimization for specific environments and applications can be done. The systems can be operated continually to ensure that no dust ever resides on the surface, or momentarily, or in some sort of pulse width modulated manner to periodically remove dust for systems that can handle some sort of or some amount of dust exposure for limited periods of time. The high voltage power supplies can be given interfaces to D-sub connectors, USB-C connectors for power and control inputs. Additionally, custom high voltage outputs have been made on different HVPS modules as well. Bare leads, insulated bare leads, I should say, SHV, MHV outputs, and a variety of other things are possible. You can see a graphic here of where this high voltage power supply plays in creating a 3-phase waveform that you saw on the EDS example from the previous slide. There's a lot going on in terms of the physics of particle movement on an EDS in general. You have a Coulomb force, you have a dielectrophoretic force, obviously gravity and drag play a role. Drag not so much in a vacuum environment, but obviously in a more terrestrial environment where there's a higher pressure of air. Friction, adhesive forces, image forces, and all of these play a role as to how particles are moved in the presence of the field generated by a high voltage power supply on a EDS. There are many ways to model this. In our lab, we spend a lot of time actually doing experiments to characterize how well different formats of the EDS work with different inputs. One big example of a test that our lab is doing is our commercial lunar payload services mission to the moon. It was launched on January 15th. This is an active dust mitigation lunar demonstration where a payload from our lab is mounted on the bottom of Firefly Aerospace's Blue Ghost 1 lander. We'll highlight here with a laser pointer where our payload is mounted on the lander. So we have a roughly 4 kilogram payload that's mounted on a fifth leg that retracts after the lander will arrive in Mons Luttrell and Mare Crisium on the near side of the moon in early March. After the fifth leg deploys from the lander, several EDSs that are a part of the payload will activate during the lunar day and potentially, time permitting, possibly during a small portion of time during the lunar night, and will be the first demonstration of this technology on the lunar surface. This project has been led by Dr. Charles Buehler and Dr. Joseph Toth here at the ESPL. Here's a close-up image of the payload mounted on the fifth leg before MLI was added to the entire lander. Here's an image of many people from the team, but not all, who contributed to the project at the launch event on January 15th. Here is a really great image from the bottom of the payload just before the lander detached from the second stage of the Falcon 9 rocket that took it into orbit. With that, I'll go back to EDS seals for a moment. So obviously with the successful mission of our Eclipse EDS mission, it will provide us data in general on EDS solutions and how well they work in the real lunar environment. And hopefully that can be applied to this particular type of expansion of the EDS technology. So the first way we looked at applying the EDS to seals was through the use of something called an encapsulated seal, or an encapsulated O-ring, for what many of you might be familiar with. So an encapsulated O-ring basically means that you're putting a layer of FEP or Teflon on the outside of an O-ring to protect it from harsh or corrosive environments. So these are sold commercially, and we thought, why not have a conductive layer underneath the insulation that's put there already to protect from harsh or corrosive environments? And therefore, that insulation doubles as a high voltage insulator for our application and allows us to integrate this sort of technology more easily into a format that folks in the sealing industry are already familiar with. So we wanted to test out just how well this would work. So we created test samples of 3, 6, and 9 millimeter outer diameter silicon rubber O-ring and Buta-N samples, and did some testing with different thicknesses of insulation on top of that to see what voltages were needed to clear dust, both from a continuous and sort of a post-clearing operation. The graphic here on the bottom right sort of illustrates what this technology encompasses. You can see the base O-ring itself, the conductive layer immediately wrapped on top of the O-ring, and the high voltage insulator, in this case, again, an FEP wrap. And all of this within the cross-section of a gland or a groove that you would see in many sealing applications. This is just a standard rectangular gland here. I'll also call out that this could also be done with a conductive elastomer. If you replace the O-ring shown sort of in an orange color here in the graphic on the bottom right, and also on the top right, or top left portion of the graphics on the right, I should say. You can create you can connect a high voltage power supply to the conductive elastomer and remove the need for a conductive wrap before the installation. So I'll go into how we set up some of these tests. We created a variety of glands that met the standard dimensions in terms of axial squeeze and gland fill that you'll find in places like the Parker O-Ring Handbook and other places. We applied a standard amount of dust for each of the test samples, meaning we placed roughly 100 milligrams of 25 to 75 micron range JSC1A lunar regolith simulant on top of each of these samples using a standardized dust shaker that we use for a number of experiments in our lab. This provided a 10 to the negative 2 grams per square centimeter aerial coverage of dust on each of these samples that you see here. The dust was applied with a 10 hertz shaker. You can see some of the samples of silicon rubber and Buna N cord stock that were cut and wrapped with a thin 91 micron aluminum foil wrap. And moving forward here a bit, here is an example of how that was placed in a mock gland. The gland was also wrapped with aluminum so that it could act as a ground layer like you would have with a bulkhead that a groove or the gland would be placed in. The gland itself was grounded, and the conductive wrap around each of the O-rings was attached to a high voltage power supply. We used Kapton tape to make the connections, or to wrap around the copper tape connections. You can see two different varieties here in the 3 millimeter and 6 millimeter outer diameter ranges here. You can see an image of many of the test samples on the left, and the dust shaker we used inside of one of our bell jar vacuum chambers, along with just a standard camera we used to look at the results as we applied dust and as we tried to clear dust from the samples. Here are some videos of just how that went. So first, I'll show you a video of the dust application on the top left. Here is a video of dust being cleared from that sample with a plus or minus 2.5 kilovolt square wave at 10 hertz being applied to the conductive part of the system. We did these tests in a way where we tested out voltages below plus or minus 2.5 kilovolts before eventually arriving to this being the minimum for this diameter and insulation thickness around this sample. We also tested out its ability to continuously clear. So the video on the bottom here shows us dropping dust and that dust being repelled before it ever hits or collects on the top of the sealing surface. Our results were to be expected based on some of the experience we have in the lab. The minimum clearing voltage increases with the O-ring diameter. That's due to the way that the electric field on the outside or between the O-ring and the grounded gland changes as a function of the diameter of the O-ring. The minimum voltage required to clear also increases, but to a lesser degree with the insulation thickness. And additionally, the continuous mode operation cleared as well or better than the exposure and then clearing off performance. You can see some data points we collected with some of these early trials here indicating that variation in minimum voltage to clear is a function of insulation thickness for different diameter O-rings. And this video is another example from a 9 millimeter O-ring here. Okay, so I mentioned before that there's another embodiment of what we're sort of referring to here as a one-phase EDS O-ring. That embodiment was where the conductive wrap is removed, and it's a simpler solution because the elastomer itself has a certain amount of conductive material in it. These sort of O-rings are sold for EMI gaskets and other things like that. So we use that and then wrap that or encapsulated that with FEP as shown in the images here. And we wanted to take our testing even further. We wanted to get a better understanding of just how much dust could be cleared with this approach. So what you see here is a 11 millimeter conductive O-ring or O-ring cord stock with FEP insulation around it before dust application. And we applied dust in this case, almost an extreme amount, I should say, with small dust capsules that we added roughly 2.4 grams of dust, which ended up being about 1.2 grams per square centimeter coverage. And we tested this at different voltages, but we found good performance at about plus or minus 6 kilovolts, again, with a 10 hertz square wave being applied. And this particular test was done at approximately 1/10 of a millitorr or 10 to the negative 4 torr in one of our vacuum chambers. I'll play the video here. You'll see an initial burst of dust being removed in just a moment. So a lot of it is removed initially, but you can sort of see here after the fact that the rest of it is taking a much longer time to eventually clear, especially at the apex of where the seals are. That's because the field is the weakest there at the top, so it's going to take a lot longer for the dust to eventually come off. But it does. If I fast forward this video toward the end here, after a little bit more than 13 minutes, you can see that most of the dust was removed. Not all of it, but most. And moving forward to the next slide here, what was removed was approximately 0.17 grams after the fact, after the EDS had done its operation. And running the math on that, it basically meant that we had at least an 88% clear rate with that 1.2 gram per square centimeter dust application. Based off of some of the results we've seen from studies out there in terms of how dust tolerant some of these seals could be with that amount of dust coverage, this is a good test. It tells us that we have a solution that can, even with that amount of dust being applied to a particular seal, we have a solution that could at least render the seal still usable even after what I think is an extreme amount relative to what you'd probably normally see on the lunar surface and in many other applications. Going further, again, with the conductive wrap solution, you can also apply this in full O-rings instead of just cord stock that had been doing up to this point for some of the samples. Here's an example of what this would look like and what the joint between the high voltage power supply and the conductive element or conductive elastomer element might look like. You can see a couple variations of this inside of a sort of dual O-ring prototype shown on the far right. We were also able to extend this as a test of just how big of an O-ring could be applied with this one-phase EDS concept. And so what you see here is a form of mock EVA hatch door, where we made a 184-inch length circumference one-phase EDS with approximately a 1/4-inch outer diameter. We placed it inside of the mock gland, and sure enough, we were able to clear dust. Here's an example or a video showing that here. This is with plus or minus 2.5 kilovolts, again, with a 10 hertz square wave. Moving forward with especially a credit out to Dr. Crystal Acosta, we were able to test out different technologies or different aspects or formulations, I should say, of EDS O-rings where we used more than one phase. Here's an example of a 3-phase concept. And the reason why we want to use 3 phases is for a couple of reasons. One, you are able to produce fields with a lower input high voltage from your high voltage power supply that allows you to clear dust without having to use potentially, plus or minus 6 kilovolts, like was shown with one of the examples before with a similar O-ring diameter. Additionally, with 3 or 4 phases, you can preferentially move the dust in a direction that you'd like. So, for instance, if you'd want to have the dust only go outward radially on a seal, this is a solution where it might allow you to do that. I'll play a video here from what this looks like. You can see in this case where the dust is preferentially moving to the right. This can be configured and optimized for other forms of sealing solutions where you may want to move the dust in something different than just outward radially or some other configuration. Additionally, we expanded this approach out to a larger scale hatch door as well, and learned a lot of lessons as to how you might want to scale this sort of approach with a multi-phase EDS O-ring. That being said, we've also conceptually looked at other configurations where you would embed conductive elastomer cord stock inside of a larger cross section. Here's an example of one design here where you have 4 different phases shown with the red, green, yellow, and black colors here. Another embodiment could be more of a rectangular cross section like you see here. again, where you have the elastomer cord stock inside the matrix, or the cross section, I should say, of rectangular seal here inside of the gland. In here, you have 1/16 of an inch outer diameter conductive elastomer cord stock and roughly a 1/2 inch by 3/4 inch cross section. So we prototyped some of this. We came up with a couple different concepts here. You can see a video operating with one of them, proving the point that even though the cross section of this is wider than some of the other O-rings before, you're able to clear dust at just above plus or minus a kilovolt, shown here with dust moving with this sub 100 micron JSC1A material on the bottom left. Here's another example with an even lower voltage, plus or minus 600 volts with sub 50 micron JSC1A in the center part here. Lastly, we did some quick prototyping to come up with an example of how this would work with an aluminum gland around it. We're working on developing a larger aluminum gland to test out this technology. But here's an example of what that looks like. In all three cases, you can see that embedding the conductive elastomer cord stock into the cross section of a full silicon rubber or other rubber format works and works fairly well. Okay, I'll move on to the next slide. We also showed the ability to mold the conductive cord stock into different geometries. Here's one example of a O-ring developed with a custom cross section with embedded elastomer cord stock as well. So that wraps up a description of some of the prototyping and development we've done on EDS gaskets to date. As a summary, the electrodynamic dust shield seals have been prototyped and tested, shown to remove lunar dust or lunar regolith simulants from rubber and encapsulating Teflon and FEP surfaces. Custom and optimized embodiments of the technology can be made for specific industries or applications, including quote unquote full elastomer solutions, where again, you'd be using conductive elastomer material. Standard, dovetail, and other seal designs are possible, as shown by some of the work we've done. Additionally, with optimization to the high voltage power supply and control optimization can also be done and readily be done for specific applications that might be outside of the lunar surface or aerospace applications. I'd like to again acknowledge the Electrostatics and Surface Physics Lab, all of the researchers we have in the lab, NASA Glenn Research Center for some of their guidance and information on some of the risks for dust on seals in general, and some guidance on how to create O-rings and some of the things we should watch out for in terms of integrating the EDS with them. The KSC Exploration Research and Technology Group, and lastly, but not least, Kennedy Space Center's Technology Transfer Program for allowing me to give this presentation and supporting the commercialization of this technology. So thank you all, and I'd be happy to answer any questions you might have.
Well, we've gotten some questions during the presentation, and we'll get to them shortly. But first, I'm going to give you a brief overview of NASA's technology transfer process. To access technologies like the self-cleaning seals through the NASA Technology Transfer Portal, the NASA Technology Transfer Program, you can search for them using NASA's Technology Transfer Portal. All of NASA's patented technologies are listed in the portal at the website shown at the bottom of the slide. You can see NASA has quite a few patents available in a lot of different categories. When you go to the portal website and begin to scroll down, you'll come to the section shown here that allows you to search for technologies using keywords. Once you enter a keyword, you'll be taken to a new page that provides you with the results of your search. In this case, the keyword used was seals, self-cleaning seals, and the self-cleaning seals technology showed up at the top of the search results. To see more information on the technology, you click on the Read More link below the technology. After clicking on the Read More, you're taken to a new page that provides a description of the technology. This is only the top portion of the description, but the Apply to License link at the top right of the page is important and will be mentioned again shortly. As you continue to scroll down the technology description page, at the bottom you'll see a Download Fact Sheet as a PDF link, which is highlighted here. Clicking on this will allow you to download the full fact sheet. You'll note that the technology description page also includes the issued patents for the technology with the links to each patent if a patent is available. This is what the downloaded PDF file for the fact sheet looks like. You'll see that it includes a description of the technology, its benefits, and applications for which it might apply. At the bottom of the second page, there's a contact information for the NASA Agency Licensing Concierge. This person can help answer your initial questions and put you in touch with the appropriate licensing specialist at the NASA Center handling the technology if you'd like to speak with someone to get additional information about the technology and discuss potential licensing. If you click on the Ask a Question link during your search, you'll be taken to a page shown here where you will fill in the information about yourself and your company and ask whatever questions you may have about the technology. This questionnaire will go directly to the NASA Agency Licensing Concierge, who will review your questions and get back to you with answers. This slide illustrates the NASA licensing process. Once you find a technology you're interested in on the portal, you can apply for a patent license through an online system called Atlas. A link to Atlas is provided in each technology description, as you saw in slide 4, where the Apply to License link was shown. Once an application is submitted and accepted in Atlas, the terms of the license agreement can be worked out with a NASA licensing specialist, and the license will then be executed between NASA and the partner. We will be taking this technology to SpaceCom 2025, which will be later in January in Orlando, Florida at NASA booth 825. We wanted to show you this so you know that we're going to be presenting this at this conference. If you have information, if you want, you can go and look it up for the conference. This QR code will give you, you can scan this QR code and it will take you to the tops in the portal.
Okay, and Aaron, we do have just a general licensing, just a question that we like to ask some of our presenters. But if a commercial company were to license this technology, what do you expect it would take for them to take this license patent to a final commercial product?
I think it would take some prototyping for their specific application, but I don't think that that would take a tremendous amount of time or resources, considering how well we know this works underneath certain conditions already. So that would, of course, depend on what application they'd like to see this applied to. There may be some challenges in that particular application that we haven't tested in our lab yet. So those would be some of the things to keep in mind. If it is a scenario that's close to what we've tested or specifically for the lunar surface in some way, I think that they could come up with a prototype that would probably be close to flight ready within a year or two would be my estimate at this time. It's very application specific, but that would be my estimate.
Okay, great, thank you. With single phase cleaning in the time-lapse video, it seemed like there were discrete events sometime after voltage is applied, where the majority of the dust was cleared. Is this correct? Do these events have a significant indicator?
So depending on the charge that the dust has on it, as it is applied to the surface or that it gets built up on the surface, maybe due to polarization or other things, that determines how well that initial turning on of the EDS clears the dust. There may be, again, it's dependent on the specific application, but you can use the system in a way where you hold the DC voltage on an EDS to polarize the particles and then turn the AC part back on. And in that manner, you can sort of get a improved performance if you don't see the type of dust clearing you want when you initially turn on the AC signal. I don't know if I'm exactly answering that question, Scott. If you, I think that's what you were kind of getting towards, but if not, feel free to add another question to maybe clarify. Maybe we can move on to the next question.
Great, thank you. Have you performed testing with somewhat moist dust instead of dry dust?
Yeah, we have. So in the past, we have characterized just how much water is in some of the regolith simulants or dirt that we're testing with. And these particular tests that I shared here today, some of them were done in air with, a relative humidity in our lab, around 50%, depending on the day. And then some were done in vacuum. And obviously the soil collects a good amount of moisture as it's in the ambient environment. So when you go down to vacuum, you lose some of that. You also have a different charge environment with the particles as well. So we've done tests in air and in vacuum. So to a degree, we have done testing with dust that is somewhat moist. I could respond with particular measurements we've done and some of the tests that have been done in the lab in the past. If the person who asked the question would like more information on that, or I could point them to papers where we've characterized some of the moisture content and some of the simulant we use.
Okay, great.
But long story short, it does work with some amount of moisture in the soil.
And if anyone has any follow-up questions for that or would like to reference any paperwork, please feel free to drop a note in the chat. So have you, let's see, did you try different frequencies than 10 hertz?
So I didn't personally for this set of testing. We would, of course, be interested in working with somebody who's looking to, get an evaluation license or a license in the technology in general to explore what frequency might be best for their particular application. But in our experience here at the ESPL, we found that the 10 hertz square wave is, for most applications, fairly optimal.
Got it.
We have done some studies in the past, and I can also point people to papers on that, where we've looked at not only square waves, but sine waves and other waveforms as a function of frequency to determine what gives the best dust clearing performance. Again, for us, the 10 hertz square wave has been fairly optimal for a lot of the lunar regolith dust clearing applications we look into.
Okay, great. Question from Griffin Lunn. Dr. Olson, what is the amperage and therefore wattage consumption of this device? Is it proportional to surface area, correct?
Yeah, there is a dependence on surface area in terms of how much power draw a particular high voltage power supply will consume. Again, we have some papers that look at this for particular configurations, 1, 2 phase, and other configurations. For all of the configurations that I showed today, even the ones going up to 184 inches in length, we were able to clear dust off of those with less than 10 watts of power consumption.
I see. You may have touched on some of these already, so maybe if you can elaborate a bit. Are mechanical properties such as sharpness or size being evaluated with the stimulant?
That's a great question. And the others have been as well. But yeah, obviously, when you look at the physics of particle movement on an EDS, there are a number of different forces to consider. And mechanical properties of a particular soil or simulant type play a role in that because of the type of friction that you have for that particle rubbing against the surface and the adhesive forces and all of that. So whether it's JSC1A or LMS1 or LHS1 or whatever the particular soil or simulant type is, they will perform differently or be cleared or moved differently on an EDS operating with a particular voltage and frequency. We've only looked at JSC1A, and BP1 simulants for this particular EDS seals technology. We plan to do more testing with some other simulants to get a better understanding of how they're moved or cleared away from this technology with time.
Okay, interesting. And let's see. dVp is proportional to the cubic or square of the particle size. Is there any size limit?
Yes. I don't know that number off the top of my head. We've tested up to, I believe, 300 micron simulant with this technology to date. I defer to a colleague of mine who I see online here, Dr. Crystal Acosta. Do you know what the largest size particles we've moved with any EDS or specifically the EDS seals technology?
So I know for glass beads, we use 1 millimeter glass beads and they move. I'm not sure about dust though, because that's a different shape. It's not like a perfect circle or sphere. But yeah, I don't know off the top of my head.
Yeah, so that's something we would work with a potential licensee to, in the way that we can through the technology transfer program, work with them to understand, you know, just what size simulant or dust can be moved. If their application has something that maybe, several millimeters in size, whether that's even practical with our application. Again, we have not tested, to my knowledge, anything greater than 300 microns with this EDS seals technology to date.
Got it. Okay, thank you for that. Next question. Did you have a chance to do seal flow tests of clean seals and compare them to seals that have had dust placed on them and cleared with the EDS technique? I guess maybe
I don't. Yeah, if that person could clarify what they mean by seal flow tests, I'm not exactly sure what that's. Yeah, if they could clarify that, that'd be useful. I don't know exactly how to answer that question.
okay. Well, we'll come back to that. Let's see. Let's go through these. For the standard deposition quantity, how long does it take to clear the dust? I know this answer may kind of vary.
Would you mind repeating that question, please?
Sure. For the standard deposition quantity, how long does it take to clear the dust?
Yeah, in some of the videos that I showed today, you can see that the dust is effectively cleared within a second. It really depends how much dust is applied, but if you mean about 100 milligrams in some of those samples from before, where I believe the dust coverage was about 10 to the negative 2 grams per square centimeter. So in that case, or about 20 milligrams per square centimeter. Yeah, in that case, it's about a second. But obviously, for the case where it was about 2.4 grams per square centimeter, that took minutes when there was that much dust application. Still clearable, not 100%, of course, but almost up to 90%. So hopefully that answers the question there.
Okay.
Standard is an interesting question. There is a dust standard, by the way. NASA Standard 1008 talks about standard methods of applying dust onto different technologies for development purposes. Yeah, but I guess it depends on what you mean by standard. In our case, our standardized tests, yeah, it was a second in one case, and then about 13 minutes in the other case, on the other extreme.
Okay, thank you for that. I'm going through to see if there's anything we haven't covered yet. Have you evaluated alternate methods of deposition, like not just light dusting, but compacting dust onto a seal, for example, by an astronaut stepping on the seal?
That's a great question. We have not. We'd like to. I think that's an interesting example of a challenging scenario where this technology, where an additional testing on this technology would be fruitful. We'll think about how to do that testing and hopefully provide some more information out there in the form of a paper when we can.
Okay, great. Let's see. Does this work for other gas environments like helium, medium vacuum, or low pressure environments such as Mars atmosphere?
So, I mean, yes, um, each gas environment is a different environment in terms of where you might have gas breakdown because of the high voltage that's applied on the EDS. So that's something to consider. It doesn't mean it's not going to work. It just means you might have other factors that are either helping particles move or potentially hindering particles moving. Um, Sort of tied on to that point and answering the question by Bevan, Bevan Court, let's see in the chat here. We have not done leak rate tests on these EDS seals yet, but that is pending, and we hope to be able to provide results on how well some varieties of these seals, EDS seals, work as a seal. Based on the minimal modification to some of them, meaning encapsulation, we don't think it will be much different than what you'd have with a standard silicon rubber O-ring or butane O-ring. But we love to have some test data to prove that. And we hope to have that data potentially before the end of the fiscal year. But when possible, we'll be able to provide an update on that.
Okay, great. See, this is a question related to applications. Can this or similar technology keep dust out of moving joints and rotating motors like robot wheels, arms, etc.?
That's a great question. I think in some applications it can be used potentially around a rotary seal where you might have a tortuous path or some multi-component rotary seal where maybe you have a tortuous path and maybe felt and all of that. Maybe this could be an application where you place the EDS seal maybe on the outside so that you get less dust intrusion into the tortuous path to start with. That's one concept that we've looked at briefly. We haven't had a chance to prototype that, but we'd love to take a look at how that might be applied in that application outside of just a more static sealing application.
Okay, well, we have a few more minutes for questions. Let's see, since the seal requires modification to insert a conductor, I assume a reduction in seal integrity at the insertion point. What typically is the expected percentage derating that you need to factor in to the maximum design pressure of the seal?
Great question. We don't know right now. We need to do some more testing for particular applications to understand what effect it has on increasing the leak rate because of an additional seal point. There are some ways of integrating this, though, that wouldn't require necessarily an intrusion. You could have a form of a contact pad or pin of some form that may not require an intrusion in the gland itself. So that's another form of applying the high voltage to the EDS seal that we're looking at. Again, that'll take some specific work on the application to figure out what might make sense there. But it's a great question. It's something that we do need to characterize.
Okay, thank you. And here's a follow-up question on particle size. This question is, I specifically need to know about how small of a particle can be cleared, not the upper limit.
Yeah, we've shown the ability to clear dust at 10 microns and potentially slightly smaller than that. Each configuration of the EDS has an optimal size of particle that it will move preferentially. And, above and below that, the performance varies. But we've shown the ability to clear dust as small as 10 microns. I don't know that we have data below 10 microns for EDS seal technology right now.
Got it. Okay. And here's another question that we missed from earlier. Could this
Actually,
be?
hold on one moment. I'd like to go back to a particular slide
Oh,
that might help with that last question. Yes, I misspoke. Slide 25 of the presentation, we did show a couple of tests there where we had sub 50 micron JSC1A and sub 100 micron JSC1A, and just about all of the dust was cleared off in that example. There is some residual fine dust in some of those cases. So if we could quantify the size range of that residual fine dust that's left, that would give us a better understanding of how we can answer that question. But it's clear that we clearly can move dust smaller than that, and I think the 10 micron range is probably a conservative limit at this point. We need more testing to give a better answer to that.
I see. And if anybody missed the earlier part of the presentation with that slide, we've recorded this webinar and we'll be sending it to everyone who registered, so you can reference that earlier slide. Okay, well, we have just enough time for one or two more questions. Could this be configured for excavation, at least on a passive manner?
Outside of the sealing application, the answer in terms of conveying is yes. Excavation, I guess that's subjective. It can transport particles to a degree. It clearly, depending on what your power requirements are for the application and other things like that, it might be a good application or good use of the technology to move material from point A to B, maybe for a soil sampling application or something like that. If you're trying to compare it to excavation like you might have with like a bucket wheel excavator or something like that, you're not going to get to the same excavation rate with this technology as you would with some of those other mechanical options. But again, soil sampling, maybe some form of conveyors, that is something our lab has looked at, and that is possible.
All right, thank you. Well, one final question before we wrap up. Did you encounter arching between the conductors across the gasket?
Yes. Not after we optimized the prototypes, but yeah, at times where we had some prototypes that had some defects in sort of creating them, we had issues at times where the insulation wasn't thick enough to basically avoid breaking through the insulator. It's something that happens in testing EDSs all the time. We adjust and modify the design to make sure we don't have any breakthrough. And then also from the other standpoint of ionizing the gas, we try to operate at a voltage where we don't run into that for the particular pressure environment that we're operating in.
I see. Well, thank you everybody for asking such great questions, and thank you for the insightful presentation, Dr. Olson. Like we said, we will be sending a recording of this webinar out to everyone who registered, so please look out for that. And if you have any interest or if you have other questions about this technology, feel free to visit this site or the QR code on the screen. There's a button to ask a question and we will get back to you with an answer. Again, we'd like to thank you for your time today, and we will hopefully see you for the next one.
Thank you all.
Thank you all.